to the first track of the day. We have File Disinfection Framework, striking back at polymorphic viruses with Mario Voksan and Tomislav Perichin.
Hello, so my name is Mario Voksan and this is Tomislav Perichin, and we are the founders of Reversing Labs. And we are here today to talk about our DARPA CFT sponsored research called File Disinfection Framework. Actually, this will be an open source project that will be released very, very soon. We are still sort of working a few more kinks, and would really love to release you full and complete set of binaries. You should probably just follow our Twitter for the full release of the binaries, but we will show you how things work today. And our goal is first to just give you a brief introduction and then really dive into our disinfection framework and really our ideas on how we deal with file infectors. So as a sort of a way of segueing into our agenda, we'll just give really brief, very subjective background and history on computer viruses, and then literally, spend a few minutes talking about problem of polymorphic viruses and file infectors, why this is important, and really why did we feel compelled to work on something like File Disinfection Framework. Once we get to the File Disinfection Framework, we'll look at two different ways disinfectors can be written. We'll look at building static file disinfectors, and then building disinfectors with an aid of an emulator that we will be releasing soon. And so I'm really, excited to finally see this happen. So as a way of a really quick introduction, people have defined computer viruses as simply a program that can replicate itself and spread from one computer to another. Very simple terms. There's a lot more complications, and we'll get into them soon. But as a way of start, let's just say that in a computer virus, there are mandatory components and some optional components. You can assume that a virus needs to find the target that it's going to infect, so it needs to search for it, and then it needs to do something with it. It needs to infect it, and then obviously in a subsequent more complex steps, it needs to be a little bit smart, apply some anti-detection rules, some anti-detection tricks as not to be detected, and really to be able to run its trigger routines now or sometimes in the future and deliver a payload. And this sort of gets us into the concept of a virus, which is really an old concept. Started a long time ago with John Neumann's research way back in '49, and we will have to fast forward to '70s when the first viruses as experimental self-replicating programs came to be. Bob Thomas from BBN Technologies came up with the Creeper virus, and it was so successful that he needed to set up a disinfection for a program called Reaper, which sort of briefly followed this DEC PDP-10 virus for a 10x operating system. Really beautiful technology, really wonderful. We obviously encourage people to do more research on it. Then we, in our view of the world, just fast forward to '84, when the term virus was coined by Frederick Cohn, where he described a computer virus as a program that can infect other programs by modifying them to include a possibly evolved copy of itself. Now you're sort of getting into the more advanced research that will, literally lead us to the sort of the file infector complexities that we have today. It would take a few years before we would start seeing more complex viruses with Vienna, the first sort of IBM platform virus, and then with Lehigh virus and a collection of boot sector viruses such as Yale, Stone, Ping Pong, and then obviously the first self-encrypting virus called Cascade. In 1990, Mark Washburn would be working on analysis Vienna and Cascade viruses and generate the first family of polymorphic viruses, or so-called chameleon family. And then not so much exciting was happening from the perspective of us talking about the disinfection process until 1998 and the appearance of the CAH virus. A virus that has been for generations, so poorly disinfected that there are today, a lot of 90s software applications, including Microsoft software that has the remnants of CA age in the various updates of the operating system present. In 2001 and 2002, zombie mistfall, or known as Z-Mist, came to be. So the metamorphic computer virus created by Zombie, the famous Russian personality, and followed by the simile virus, a metamorphic virus written in assembly. So this sort of segue leads us into the really the file infection problem that we will be addressing today, and why are these polymorphic viruses important? And so we view the file infection at the endpoint as really the ultimate polymorphism. It's a situation where an infector replicates itself into a host of unique, different containers, where one strain can generate literally hundreds of thousands of unique infected samples. So we all deal with massive amounts of samples today. What's the big deal with more of the same? The idea is we can't just write signatures or ban files one by one. We really have to come up with a more organized response. And response is really quite difficult because you really need to reduce the huge quantity of samples into a single infection, single situation that you will be looking at, that you need to identify and find a generic or specific way to excise, disinfect items. As usually machines have multiple infections, and if you look at things like virutensality, those are really the conduits for bringing more infections to the endpoint, and it's not unusual that a single file has multiple infections within it. So the question is, what do you infect from what and in what order? So this infection really becomes like a surgery, very delicate, very exact process where if the offending payload is not properly removed, bad things happen. So not just that, you could, the very basic level, forget to remove the malignant content, and the infection will simply come back, which happens very frequently with, again, this, sality and virut infections. And then also, it's very, very important, that once the extraction has happened, that the incision areas, the sutures are applied correctly so that the file can actually be executed, that it can actually work again. And if this is not done correctly, if this has issues, and there has been quite a few pretty bad disinfection modules written in the past where the worst case scenarios happened, like the system downtime or loss of data, and then obviously the more simply reinfection in a week or two. So file infectors usually bring significant dilemma, to those who are infected, be it in enterprise or being consumer. So the choice is pretty simple. Do I try to disinfect my system, or I simply go ahead and re-image? And the responses are usually quite different. So consumers always prefer to disinfect, rarely re-image, because they're attached to their machine. They're likely not backing up frequently enough or at all. They have a lot of personal data on those machines, lots of media, which will always trump any security risk. I want my stuff, and I will try any kind of tool before I resort to reimaging. And these users are today served by their AV products, largely free AV products, but AV products, for getting that disinfection done. Now, on the enterprise side, the logic is a lot different. The IT department will prefer to re-image the system, if at all possible. But it may come with a really hefty price, because it may not be practical in all the cases. So you can imagine if you have a massive infection over 10,000 or even more units, if your IT staff is 3 or 4 people, you really could end up with a mutinous type of situation where disinfection is definitely a step that you would like to try before re-imaging machines and potentially losing the entire team. I've heard of situations where people simply quit because no one's really looking forward re-imaging tens of thousands of machines for the next month or 2, only to know that there was a leftover major infection that would come back, like it happens again frequently with these virus and sality infectors, to undo the job being done. So the only problem here is when you offer enterprise disinfection route is who will write these disinfectors for the enterprise? And so this sort of brings us closer to understanding why did we went down the path of building something very complex. Why did we pitch to DARPA the idea of working on a specialized framework that would allow people to build better disinfection tools quicker? So simply, the purpose of this was, after speaking to a lot of different researchers in different organizations, not just AV, over the last few years, them complaining about not having enough time to test, not having enough resources to test their disinfection routines, and then bad things happen that nobody's afraid of. Because after all, we are here to protect people, not to destroy their stuff. So when the destruction happens, it's definitely not something that we're happy about. So the purpose of this framework will be the speed of development, increasing the quality, reducing the chance for a risk of failure, improving the test process, and then finally creating something that really is lacking in industry, and that's the ability to collaborate around some of these very, very important modules, giving out not just the modules but the source code, hoping that people can modify it for all the similar strains of a particular attack that we are looking at. And so the benefactor for this are, so not only the AV companies, but also the CERT teams that are increasingly working on projects where they're responsible not only to detect, inform, but to remediate and bring their constituents, to a good state. ISPs are increasingly being told that it's really not acceptable that they're having botnets at 1 million, 2 million, even more millions of endpoints infected. And they really need to start doing more to affect a solution that has not been served by AV. And AV is very, very specific in that will always work on the solutions that affect the majority of their population. And so that, if you're enterprise, if you're part of an exotic ASP that was targeted by something quite specific, you may not fall into that category. And then obviously, we will be seeing enterprises taking the security in their hands as we're seeing today with increasing binary inspection, both of a static and dynamic kind. We will be seeing in the future people writing their own disinfectors to help themselves. All right, so without further ado, I'd like to ask Tomislav to actually get into the weeds of it and talk about the File Disinfection Framework. Thank you. No. Test.
Okay. My name is Tomislav Perichin. I'm the Chief Software Architect at Reversing Labs Corporation, and I'm here today to talk to you about the File Disinfection Framework that we are presenting. So the File Disinfection Framework has been described by my colleague, and at its heart, we have an engine we call the TitanEngine. Now, the TitanEngine is an open source library which does portable executable file manipulation. And throughout its history, it went through all sorts of iterations. So just for historic purposes, we keep this slide to remind ourselves how much time we actually spent working on this library. So what you see on this one slide is about 6 years of development. So the first version 1.0 is a historic one. We wrote that in assembler just as a proof of concept. We mainly focused on dynamic unpacking solutions at the time, so it only used the Windows Debug API to actually process files. The version 2.0, which we actually presented here at Black Hat in 2009, was a total rewrite from assembly to C. We had a lot of improvements and a lot of functionality which enabled you to work with those files even better. The version 3.0 was presented recently at Hack in the Box in Amsterdam, so this year. That was a total rewrite from C to C++, and it was focused mainly on static file processing, because we believe that static file processing is the way to go if you want to have a safe environment where you can do all sorts of file processing operations really, really quickly. So expanding on that, we have a version 3.1, which we're talking about today, and we're actually presenting it today. So in addition to all these static functions, we expanded those static functions to enable you to disinfect files. And in addition to that, we added an x86 emulator, which enables you to basically run polymorphic viruses inside a safe environment for as long as you like until the process of disinfection is complete. So what is the File Disinfection Framework? So that's an open source library which you can use. So for now, it's version 3.1 is for Windows, x86 and x64 builds are available. We will be porting this to Linux really, really soon. So next month we will have a Linux build as well, so you can run that on your favorite distribution. It enables you to do static file manipulations, integrity checks, and recovery. You can build dynamic files, portable executable files on the fly. You can recover imports with hash databases. You can create decryptors dynamically, and you have the advanced x86 emulator, which is really unique, and we're really proud to show it today. So here are some statistics about the code, so you get the idea of how much work went into this. So we started this project about a year ago. Right now we have over 100 user-exposed APIs which you can use to do all sorts of manipulations, and we have about 40,000 lines of C++ code. So it's a really huge project, and we have a bunch of features lined up for the rest of the year. So the engine itself consists of two parts. One is the static file disinfection part, and the other one is the emulator. So for the static file disinfection, you have an ability to actually read portable executable files, to modify their content, to read individual sections, merge, split them, create new ones. The same story goes for portable executable tables. Embedded inside it is also a support for a large number of decompression algorithms. So if you come into a problem where you have to actually decompress data, you have that available as well. You can build custom dynamic decryptors. We're going to talk about that a bit later, as well as how do you use hash databases and why. What's really important is how do we approach file format validation, especially because viruses have a tendency of damaging files during the infection process. So we want to be sure that not only the file is valid before we start the disinfection process, that we actually end up with a file which is always valid, because the idea is stripping out the virus directly from the file, and not only that, having it in a runnable state. So how do you work with files with the TitanEngine, or more specifically with the File Disinfection Framework? So you have an option of doing all sorts of manipulation, like when you open the file is read directly from disk, and the sections are mapped in memory only when needed. So only when you're changing the content is changed directly in memory. This is to ensure that no specific part of the virus can actually escape the environment in which you're working on until you have cleaned the entire virus from the file. So all the modifications you do are done in memory up until the point that you decided that virus is now eliminated from the file and you want to save these changes to disk. And as soon as you start saving these changes to disk, the file is rebuilt entirely. This is to make sure that the file is valid, that all of the imports, exports, and other features of the portable executable file format are intact. So what can you do with the portable executable file? So speaking about the portable executable tables, you can create, view, and edit the existing import, export, relocation, resource, TLS tables, and the overlay. So you can create new ones as you see fit. And for the other tables like bound, import table, delay import table, exception, and debug, you can just view or enumerate them. We didn't feel that those tables were necessary to be included in the rebuilding process because they cannot hold the data which viruses usually use. So how do you enumerate data? And this is really important. Enumerating data can happen with user callbacks or with serialization. So you can use one or the other approach. The callbacks are used because there can be a lot of data in the PE files. Those strings can be basically indefinitely long. And to avoid the issue of using too much memory, then you can use callbacks to enumerate one entry at a time. If you prefer to have all that data available to you right away, then you can use the message pack serialization, which is included in the package. So how do you create a new PE file, and why would you want to do that in the first place? So creating PE files is really important because it comes into play when you are disinfecting files. You have an option of building a new disinfected file from scratch, or you can use the features which are present in the file itself to recreate the file itself. This also comes into play later on when we talk about the emulator, but we'll get to that in a bit. So how do you create files? Basically, this is a list of APIs you have here on the slides, and there's no need to actually read this right now. Just focus on the concepts, which are really important. So the slides are there to help you out when you actually start working, and then you have everything in one place. So create file actually creates a new portable executable 32 or 64-bit file in memory. No sections exist at this point, but if you want to, you can add certain features to it. You can edit the portable header, which is already present as soon as you create the file. So you can set the image base, original entry point address, whatever you need at that particular time. However, there are really no sections. You have to add them. So right here in the example, you have a specific section for a specific part of the portable executable. So there's a bunch of these, and it's the same process. Adding a new section is just calling add new section, which creates a new section of your desired size. Getting content is reading data from that section, and setting content is really writing data to that section. Now, the important part of this is that all of the changes you do are done in memory. And this enables us to do the following thing. If your section is the last section of the file, then writing past its end will actually increase it automatically. So you have that neat option of working its sections as they are shown on the slide, as they are linearly linked. So if you imagine that you want to read data directly from code and import section at the same time, you can just do that if you point back to the code section. So they're really working together as they are when files actually execute. So this comes as a limit, and the limit is as soon as you modify something in a section, then the data is read from this, committed in memory, but those changes you did are lost. To work around this, because you might want to go back and read some data which you didn't think that you needed at that particular time, then you can access this data as well. So if you read physically from the file, so from physical offsets, then you will be actually reading from the file on disk. If you're reading from the relative virtual offsets, you're reading from the current changes in memory. And that's really important concept to grasp, because you want to be working with memory all the time, because memory is fast and you don't need a lot of it to accomplish your task. So additional features that portable executable files can have are import tables. Now, to build a new import table with this specific import address table, you call a few APIs. One is to add library to the import table tree, that's add import library. You want to add more functions to it, that's add import functions. And then when you're done building the entire import table tree, you just write that to wherever you want. Here we created a new section and we just host the import table there. Same story goes for relocations and resources later on. So you basically just add base relocations for every address you want to relocate. And when you're done with adding all the addresses which need to be relocated, you just write that table. Same story goes for the resources. You add resources, and resources can be added by name, type, language, code page, and so on. That's all the data you can customize, including what the actual resource is. So as soon as you add that data to the resource section, you can just write it, and you have the valid resource table. And then at the end, overlay is just append the data to the end of the file. You can use the function called find overlay to check if the file actually has overlay. If you want to add more data, you can just add overlay. And as soon as you start adding data, it is added one after another inside the overlay. Once you actually start saving the file, you have an option of stripping the overlay or specific overlay parts, such as the debug table or certificates, because when you create a new file, that digital certificate is no longer valid because the file has changed. So you might as well strip it. So let's say you built this file and the file is now complete as it is on the slide. The only thing left to do is save it to disk, and you call export file to save everything you've done with your file directly on disk. File is reconstructed, so all the section content has been committed from memory to disk, and we make sure that it's valid, so you make no mistakes of actually reconstructing the file. So that brings us to our first virus. We're going to talk about two specific viruses. This one is called Win32 Awful, and it really is awful. It's a play on words, but AV guys back in the day made these kinds of names for a reason, and you're going to see why. So this specific virus has a couple of names and it has a couple of versions. It only infects portable executable files, more specifically executables and the screensavers. So it doesn't work on dynamic link libraries. Has a couple of versions, and back in the day, the versions the files were versioned by the size of the virus code itself. So as you can see, the file size grows, and so the virus is improved. And the comment is that it actually is awful, and you'll see why. The entire virus is just appended to the end of the file. And the original entry point from the original file is encrypted. So that's the data we need. We need that original entry point so we can remove the virus and restore the file. There are some anti-reversing protections, like is debugger present and create file A for soft X checks. It uses Visual Basic scripts to infect other Visual Basic script files, but we're not focusing on that. Why is it awful? Well, it has a couple of bugs which are really bad. At the beginning of the virus, it uses the movie SI instruction to locate what's the part of the file which it needs to decrypt. However, the author of the virus made a mistake, and it's not pointing to the offset where you have to start the decryption. It's actually reading data from that offset. So that's why that virus wouldn't work, and that's one of the first versions. In the later versions, debugger checks don't really work because it doesn't check the API return. It just checks the zero flag for the is debugger present, and that clearly doesn't work. It really can't find other files to infect because of the wrong parameters set for searching the files, and it doesn't close handles properly, and it destroys the original overlay of the file. So why are we talking about this? So we're talking about this because this isn't a lone exception. There are a lot of viruses with really damaged files that are not written in a good manner, and that's why we need to support them as well, because you have to be able to recover from any kind of infection for a system. And this is one of those representatives where it can get really hard because the author of the virus basically didn't know what they're doing at that time. So how do we do this? How do we create a disinfection routine with our file disinfection framework? So first and foremost, we check if the file has been infected. And that means two things. Either the file has been infected and you know the exact version of the file, of the virus, and or it's a virus body. Now, virus body is just a carrier. It's not an infected file, it's the virus itself. Once you run that virus, it starts infecting other files. And once those files are infected, they start infecting other files as well. So we have to differentiate between the virus body and the infected file. So once we do that, we get the virus code delta, because all the viruses have been created to be offset independent, and that is quite logical because they can be anywhere in the file. You have to get that starting point somehow, and that's called the virus code delta. It's usually stored in the EBP register for these old viruses, but new ones use other registers as well. So then we have to decrypt the virus body, read the original entry point address, resize the last section, effectively eliminating the virus, updating the P header with the original entry point address, and saving the disinfected file. And that's it. Those are all the steps we need to do for this virus. So how do we decrypt that data? If you look at the slide, it says virus entry point, and the virus entry point is not actually encrypted. And there's a bit of the code which is not yet encrypted. So I'm going to switch back to my VM just to show you how this looks like. So here is one of those awful viruses. And this is actually a virus body. So here you're going to see the entire code without actually the encrypted part. So here is how the virus body starts. And if you look at this part right here, this is a little loop which actually decrypts data. Everything behind that point is actually encrypted if the file is infected. Now this is a virus body, and this is how we can easily differentiate between the virus body and the infected file. Now if I scroll down through this file, you're going to see that it's not a lot of code, but it is infecting other files. This is the place inside the virus body and the infected file where you store the original entry point of the infected file or the virus itself. So here is the code which we need to read to actually disinfect the file. So that's the original entry point address. So moving back to the slides, we know that the code can be encrypted. So how do we actually decrypt it? For this particular virus, the code is not polymorphic. However, all the techniques I'm going to show apply to both polymorphic and these normal viruses as well. So once we decrypt the data, we have to verify if decryption has succeeded. And the decryption always succeeds if we can find other data which we need to read, and that's the original entry point address. So here is how that actually works. I'm going to show you how the disinfector works before we go into how do we create the specific disinfector for this. So here I have a command line and it shows the following thing. I'm just running my application which is running the FDF framework which tries to disinfect the file. So when I run it on the file, it says the file is a virus body. So the identification part has been embedded. So we check if the file is a virus body. If the file is a virus body, then you don't have to do disinfection. You can just delete the file because that's the virus itself. However, the files can be also infected, and I have the file right here which is infected. So this is a normal application. It has been infected with this particular virus, and once we disinfect it, it says we successfully disinfected it, which means we completely removed the virus. So once we actually take a look at the file right here, so this is the disinfected one, I can just actually run it because we removed all the traces from of the virus itself. There is no traces of the virus, and the file is exactly as it was before infection. Some things have been changed during the rebuilding process, but the file is actually correct. You can see all the code, you can see all the imports right there. So that's the goal of the File Disinfection Framework, is to actually remove all traces of the virus so we are able to recover those files from being infected. So decryptors help us with that because most viruses have encrypted bodies, and that code can be either normal, so it's a pre-built routine which does the encryption, or it's polymorphic. But the same story goes. You can dynamically create these decryptors which actually enable you to decrypt data. And decryption is performed both forward and backward as any way you actually need it, and it's performed in steps of 1, 2, 4, or 8 bytes. So the decrypting virtual machine is a virtual machine you program with structures, and it can consist of both x86 and x64-bit code. So how does this code look like? We have one element right there. So let's say I want to emulate the instruction move AL byte pointer, whatever is the current encrypted byte I'm decrypting. So that's the instruction I want to create. So that's the structure you have to fill in. So the opcode is move. The opcode type is target is register because we are moving to AL, and we're moving from the encrypted byte. So source is memory and it's 1 byte in size. So that is the opcode type. The opcode target is the AL register. Source is none because we're reading from memory, and we don't have any immediate values. So for this specific virus, so for awful, we have to create a specific decryptor. Now this can be created both dynamically, or you can create it statically. Because this virus doesn't change this decryption routine, we don't need to build it dynamically. If we were decrypting any polymorphic virus, then we have a disassembler embedded inside the TitanEngine or the File Disinfection Framework, and you can dynamically build these by disassembling opcodes and translating that to our virtual machine code. So once you do that, you actually run this inside our virtual machine for a number of times. The number of times is specified in the virus code, so that's ECX register's value. So to create a dynamic decryptor, you just call create decryptor, which creates a new handle for you, to which you add code. The code you add can be stored in two streams. One is the initialization stream, which is executed only once, and the other one is the actual code stream, which is executed for every pass of the decryption loop. And the decryption loop occurs ECX times. So once you actually decrypt data with call to the decrypt data API, all the code has been decrypted. So here are more complex examples of what you can actually do with this specific part of the virtual machine. So you can create jumps as well. So as you can see, the line number 3 actually jumps to the label. So you can jump to that label just by creating an instruction that way. Similar story goes for the stack. The stack is also available, and the ESP register is modified. And if you want to communicate with the decryptor as decryption is going on, you can just use the call instruction to call your predefined callback, and from which you can change the register state, or you can manipulate the encrypted data itself. So you can communicate with this in multiple forms. You can also set a trap flag, which does what trap flags do. It executes, it calls your callback for every instruction which gets executed. So that brings us to the emulator. The virtual machine I spoke about right now is the part which you can use for static disinfections. However, if you want to run the application inside a safe environment and run its entire thing until it basically decrypts itself in memory, so you can dump it and fix it, then you have to use the emulator, because the emulator gives you an option of actually running this code in a safe environment. So what do we emulate? We emulate the basic x64 Windows environment. That means process environment block, thread environment block, sec structures. We also emulate user mode libraries. For now, we support over 100 functions, which are most commonly used in viruses for kernel 32 and user 32 DLL libraries. If the virus needs something that we do not support yet, you can easily add that. You have an option of dynamically building PE files, which we spoke about at the beginning of the talk, and you can just inject those directly inside the emulated environment, letting the emulator load that as necessary. Or you can dynamically build those dynamic link libraries from hash databases. We'll get into that in a minute. So we emulate that. We also emulate the file system, because we have to let those viruses actually infect other files and run themselves. So we emulate that. You have an option of customizing the environment by adding new drives, setting the size of that drive, such as the type, size, name, label, and so on. We support file mapping, attributes, timestamps, and file shares, because those are the things which viruses actually use. We support multiple breakpoints, so you can track this code as it executes, and it works as you would expect from Windows Debug API. So what we try to do is mimic how Windows Debug API works, so you're more comfortable with the actual API itself. And this is what separates this framework from everything else, because you can actually run high-level code inside the emulated environment. And I'm going to show you how that looks like in a bit. So before we actually start the emulator, we have to load the file. So opening the file does what we said before. It just maps the file in memory, and all the sections are committed in memory. So once the actual process is created, before we actually get to that, we have to figure out if the file is valid or not. So if the file goes through the validation process and it has been deemed as damaged, but we can repair it, then you can use the repair file API to recover these damages. All these damages have been recovered in memory, so when your emulator starts, you can actually work on the file, because the file is now valid, and you can load other files and do whatever it needs to do. So once the file is okay and the emulator can actually load it, then you can create a process. We can create that process, and that works like on Windows. Everything's basically mirroring the functionality of Windows. So the newly created process loads other dependencies, it relocates itself if necessary, maps itself in memory, and so on. It does all the things that you expect the process to do. So that's why this is an emulator. We're emulating the Windows environment for the viruses to actually run inside them. So how do you run the emulator? You just call run process, and run process actually starts executing those opcodes. And while you're executing opcodes, there's a list of events that can happen inside a virtual machine, which actually connect back to your callbacks. So these debug event code callbacks types are the same ones that you would find in Windows. So you can have a notification when a new thread has been created, when a new process has been created, dependencies loaded or unloaded, and so on. We have one additional event, which is the initialize debug event. This is before the actual process has started inside the emulator, and that is to allow you to copy all the files to the virtual environment and do all the initialization processes that you would need for the actual virus to run. So one of those things which are required are actually dependencies. And dependencies are dynamic link libraries which are statically imported by the application itself. They can be statically loaded, and they can be also dynamically loaded. There's a predefined list of the things we support, but you can extend this easily with hash databases, or you can dynamically build new portable executable files. That really depends on the use case scenario. So what are these hash databases? They are user-created files that basically have a list of model exported functions. So if you need to emulate an API, let's say from kernel 32 DLL, then you can run our tool on kernel 32 DLL, which creates a database for that file. And that database has all of the exports of kernel 32 DLL. So once the emulator starts loading the process and it needs a kernel 32 DLL module loaded, it just checks all the databases it has available, and you can push as many as you like. And once it finds the module it's required, then it dynamically creates this portable executable for you in memory. So if the application actually calls these exports from kernel 32 DLL, they're actually there. So that's the idea. It's called a hash database because all the entries are stored by function name inside it, but there's also a list of hashes. Now this list of hashes is really important because it enables us to recover those hashes from the hash itself back to the original string. And that's very important for viruses because viruses usually do function lookups by hash itself. So once you see a hash, you can just revert that back to the original function name. Now there's a problem with this. The problem with this is there's a preset number of hashes, and the algorithms used by viruses are custom, which is why we added the support for you to actually add new hash algorithms to the databases themselves. So just like you would create a decryptor, you would create a new algorithm which gets stored in the actual database, and that actually produces the hash. So you have that as well. So that is using the hash databases and all the use case scenarios. So once you actually have that library inside the process, you have to work with those functions somehow. And as I said, we support a lot of functions, about 100, which are most commonly used by viruses. But let's say you want to do something when a specific function is called. Then you can install a hook. And the hook works in a few different ways. So once the emulator starts emulating and it gets to the API we support, so let's say that's get model handle A API, and you install the hook to that API. So as soon as that API is called, your callback gets called, which means that you can do any kind of code before the actual API is executed. Then the function is executed inside the emulator. So get model handle A really returns the handle for that DLL. And then you can additionally have an additional set of post-call hooks which take the return from that function and do other manipulations on it. So you can hook before the function, after the function, and you can even replace the functionality itself. So let's say we made a bug and our API doesn't work and you just want to replace it, or you have an API which we don't support yet, so we can just define it by yourselves. And that is just replacing that API with your code which executes inside the context of the virtual machine. So as long as process is executing, there are some breakpoints being set here and there because you need to monitor that process. And the breakpoints we can set in our emulator are really good for file analysis and file disinfections in general. So you can set the breakpoint on page access, any kind of access, on address, and on instruction itself. So the instruction itself, you can basically set a breakpoint on every move command. And it's one of the examples I'm going to show you. So the breakpoint types can be also combined with specific actions, like I want a breakpoint when this address is read from, or written to, or executed. You can just combine those conditions to create all sorts of scenarios which match your use case scenario. And they can execute once or multiple times. And once the breakpoints are removed, they can be, your callback can also be notified. You can have multiple breakpoints on the same address, and they will not overlap with each other. The same story goes for any kind of breakpoint type. So here is an example of a complex breakpoint you can have. So let's say we want to create a breakpoint on an every move instruction that tries to write to a specific range. And this is how you do it. You call this API and you say, okay, create this breakpoint, have it execute always, action is write, address, and instruction. So as long as you have a move instruction writing to the specific range, then your callback will be called. And this is much better than any kind of debugger because you can set any kind of condition and combine these conditions together to get the desired effect. So last but not least are exceptions, and exceptions work exactly the same as you would expect them to work. As soon as the exception is triggered, the exception chain is went through until you find the appropriate structured exception handler, which actually deals with the exception. But the exceptions are first and foremost pushed to the debugger itself or the emulator, and then the emulator decides what to do with it. So if there's an internal exception which is handled by the application itself, you can just pass it, or you can handle what happens on that exception. And here's the cool bit, because our emulator supports so and so many instructions. And let's say we don't support an instruction yet. If we don't support an instruction, we're just going to throw you an exception which says we don't support this instruction. And then you can define what happens on that instruction, and then you can just pass on that exception. And then you can easily extend this framework from the API standpoint. You don't have to go to the source code. That was our idea when we started designing this. So there's the symbiosis between emulator and the static environment, and we really wanted to create it like this because it enables us to do a lot of things. So if on the left side you have the file on disk, and you loaded that file into a new process, and the process is shown on the left side, whatever happens with the process while the application is being emulated is reflected back to the original file. And that's fine because viruses cannot escape from the emulated environment because the files they're infecting are still in memory. They don't exist for real until you decide to save them. And you can decide to save them at any given point. So everything that happens in the emulator reflects the file you're currently working on, and that is something we will be using to this effect the next virus. So you can execute high-level code inside this, and this is really important because let's say you don't want to start emulation from the entry point of the file. You want to start from a specific function. Then you can use these APIs, which are basically whatever you expect from Windows, like create file, write file, read file. That's the file system API. There's other types which read from process memory, allocate memory, and do other things as well, handle mutexes, and so on. There's a lot of these APIs. So you can set the environment any way you want. You can create new files on the disk which the virus can infect. And here's the example of that. You can mount a new drive in the system with mount drive. So let's say I create a floppy drive on my system. And on the floppy drive, I just import a file from my host system. That's like a bait file or anything like that. I can even dynamically create it and put that on the floppy. Then I run the emulated process and wait for the virus to actually infect this. I can check if the file has been infected by timestamps, by file sizes, anything you would normally do. And you can also check if the file handles have been closed, and so you can actually read it. So once you do that and you have infected the file, you can do basically a diff between those two files and see what has changed. If you're happy with the results, you can just copy that file directly from the virtual system, directly to the host system as well. So Virit. Virit is one of those polymorphic viruses which is really complex. The sample I'm going to show you today is one of those really complex viruses, and I'm going to show you how it works and how we created a disinfector for it. So what is Virit? So Virit is a portable executable file infector. It has a backdoor, it's memory resident, it has a couple of aliases, it has a few different versions. So we selected just one version for the purpose of this talk, and we created a disinfector for it. That's going to be included with the SDK itself. So yeah, how does the virus actually behaves? So the original entry point is moved, and it's actually overwritten with the virus code. So once the virus code is at the original entry point, then you have to revert back that when you actually are disinfecting the file. So virus body is yet again at the end of the file, so you will be reducing the size of the file as you're disinfecting it, and you will be copying back the original entry point back to its original location. So that's all the steps we need to do. We have to determine the virus version. We specifically made this for one specific version. Determine if it's the virus body. If it's not, we have to disinfect the file. Same steps as before. Get the virus code delta, read the original entry point, get the original entry point address, update the original entry point, resize the last section, update the P header, save the file. So those are all the steps you need to do. And here is the log of our virtual machine. So this is actually running a virtual machine. As you can see, events happen and events are logged. So you have the create process debug event, which happens when you start the emulated environment. You have all these load DLL debug events, because DLLs are being loaded inside this virtual environment. And here, the last one is the actual breakpoint, which happens when you actually disinfect the file. So I've placed just one breakpoint, and that one breakpoint was enough for me to disinfect the file. So I placed a breakpoint on the return instruction, because Virit in every version of its code has 2 returns before the virus code is decrypted. So I wanted to be able to break on the second return, get the data from the decrypted body of the virus, update that to the original file, and then strip the virus. Here are some stats about the disinfection. So where are all the data inside the file itself? Now I ran this before we started this presentation. It actually took 5 minutes to execute. And that's really bad if you're looking at disinfecting a lot of files. However, there's a really good reason for this. Number one, this is a debug build, so it's slower than usual. And other than that, there's a lot of libraries being loaded, but the number of instructions being executed is just huge. We have to execute 245 million different instructions to actually decrypt the virus itself. So at this point, as we are presenting this, our current average emulator speed is about 1,000 instructions per millisecond, and that's not good enough. We can actually optimize that, and before the release we will actually tenfold this number, so you'll have 10,000 instructions per millisecond, which will reduce this disinfection time by tenfold. And there's a really good point is, you should not be running this much code. There's other features inside the library itself which can actually help you deal with polymorphic code. It's a bit more trickier to use. However, if you want performance, that's the way to go. If you want to just run the virus until it decrypts itself, then you have to deal with these kinds of penalties. We will further optimize the speed. However, there are limitations that yet remain. So once we disinfect the file, I'm going to show you first how the infected file looks like, and then I'm going to show you how the disinfected file looks like. So I have one sample here which I previously analyzed, and this is the one. And you're going to see why I've chosen that return. So when I scroll through the code, and the end of this first layer, you're going to see return. So this return and all the code before that is the original entry point. It just replaced by the virus code. So if I run until this point and just step over that, this is the actual virus itself. That decrypts the virus itself, and the virus itself, once decrypted, is executed after the next return. So I'm just scrolling down to find the next return. It doesn't matter where the return is, as long as the return is executed, then the actual code will be decrypted. So here I'm just scrolling, there's a lot of code, and there's a reason why this executes 245 million instructions, because there's a lot of duplication. The decryption happens all over the place. So once Okay. Once this return is hit, you can see the virus body. Now the virus stub is actually quite straightforward, and it does all the infection parts. So here at the end of it, you have the original entry point code, which has been encrypted by the actual virus itself. So this is the part right here, which you have to copy back to the original entry point. So once you actually disinfect the file, I'm going to show you how that looks like. And the file is yet again stored in a runnable state. You can just run it as soon as you decrypt the virus. So disinfected, that's the file I created during the talk. And I'm copying back that to the virtual machine, and I'm going to show you how that looks like right now. So this would be the disinfected file. So there it is. That's the original entry point. You can just run this file if you like. So that would be TitanEngine 3.1 with the File Disinfection Framework included. You can get it at this address really, really soon. We hope to get it published by the next week. We have a lot of future plans for this. 3.2 version, which is coming by the end of next month as well, will be ported to Linux. You will be able to run this code on Linux, both 32 bits and 64 bits as well. We're actually not happy with the disassembler and assembler functions embedded inside it. We're using an open source solution which has a few bugs and causes some few issues. So we will be replacing that with our own code really soon. And we're implementing Title language, which actually enables you to write custom signatures to identify files. Right now you can do that as well. There are functions inside the TitanEngine which enable you to disassemble opcodes, match them, and do any kind of pattern matching you like. This is just going to be much better because you're going to be able to do this in a scriptable manner. So that would be the File Disinfection Framework. We're happy to take your questions right now. So yeah.
This one's really simple. It may even be obvious. When you've taken a file that's been possibly damaged by the virus, you bring it into your framework, you recreate all the parts of the PE file, write it out again. The result is going to be fully functional, but it won't necessarily be identical to the original. Is that correct?
Yes, that is correct.
Yeah, that actually is my question. How far off are you, how far off is the reconstructed file from the original file?
It really depends on the virus itself. It doesn't matter what the offsets are. The entire code, imports, and everything else is there. The file is functional. It could be in another section or anything like that, depending on what you're actually doing. However, it really depends on the virus. It doesn't matter as long as the file is functioning. That's the goal. So it doesn't have to be the binary identical copy. That's probably impossible. In some cases, it's really possible. For awful, as we saw it before, that is actually the binary identical copy. However, the awful is awful, and it infected the file and removed the overlay, and that's why the file is not binary identical. That's the problem.
Do you have any intuition into how often you actually get back to your original file?
Really, really often. It really depends on the virus itself, but for the most simple ones, were it included, the reverted state is 99% equal to the original. But it can drop down in specific cases.
Have you run into any viruses that have detected the presence of the trap flag being set and that do something different because of that?
Well, it really, we don't use trap flags at all, but we, as an emulator, we have an option of controlling everything that happens in there. So if there's an opcode which detects your environment, you can just easily avert that because you're executing every instruction, you're executing every function, you can control the returns from the function itself. Anybody else?
For why have you decrypted it and linked it without emulation? As you said that you have some APIs available in your framework without doing the 225 million?
You don't have to execute the virus part which actually infects other files. We just had to get to the part where the virus is decrypted itself. We can actually execute the infection components, the backdoor components, if we define those functions as well. Like it uses the registry keys, which are not yet defined in our framework. There will be soon enough.
So did you find any way to not execute those 225 million
Yes. You can really shorten this 245 million instructions to really smaller subset. I'm just trying to show you the example of what you can actually do and how fast you can do it. And this is a really good stress test. In a real world scenario, you wouldn't really be emulating nearly as much instructions, just the small part which actually does the decryption. Or you can do binary rewriting and rewrite that to the original decryptor, which will be executed much, much faster. So it really depends on what you're actually dealing with. So for the purpose of the presentation, I didn't want to do binary rewriting because of the speed, because we wanted to show the emulator part. And the emulator works in that kind of way. More questions? If that's it, we thank you very much for your attention and wish you nice reminder of the conference. So enjoy. Thank you.